welcome to the course on power quality. We were discussing the improved power quality multipulse AC/DC converter. So, we will discuss today the analysis of multipulse uncontrolled and control converters, which consist of diode and thyristors. And you can have it here starting from, let us say we can have a 12 pulse converter, which have a 2 converter. I mean, like normally it is with the transformer, phase shifting transformer, and many applications we require the isolation, because the utility voltage may be quite different than what at which we have a application. Then this is typical. So, we need 2 converter, as we discussed last time, that we require 60 divided by, I mean, like number of converters, like so in 12 pulse you have a 2 converters. So, it will require 30 degree phase shift between the 2 sets of winding, and that is the reason we call it like a phase shifting transformer. I mean, typically between the 2 sets of 30 degree, like I mean, which can be obtained by either plus minus 7.5 degree or 0 to 30 degree or 0 to minus 30 degree, many way to get it. And we have discussed lot of transformer connections which are possible for 3 phase to get this phase shift. Like then in 18 pulse, of course, we require 3 converters, I mean that is, and the phase shift requires 60 by 3, that is a 20 degree. So, you can have a plus minus 20 and 0 degree, and that is the reason you have a 3 converter in 18 pulse, and 24 pulse which require have a 4 converter, and 6 pulse 4 converter here, and you can have typically 60 by 4 15 degree phase shift between them, maybe plus minus 7.5 degree or then 22 plus minus. So, and output of these, because since they are isolated, you can connect either them either in series or parallel to have a typically according to your requirement what DC voltage you want to get from them. So, coming to the first topology, I mean like where we have a this 12 pulse series type diode rectifier topology, and you have a 2 converter of 6 pulse which are connected in series. We are deriving virtually like a, you can call it the voltage applied to the next application. Mostly these converters are used for variable frequency drive, maybe with the induction motor or any other like a synchronous motor or so, to where at the input we use it. And we have a here the 30 degree phase shift because of your star star connection, 0 phase shift and 0 delta. So, that is we get 30 degree phase shift. So, that serves the purpose for phase shifting, and you are able to get, because of this phase shift, 30 pulses, 12 pulses in the output voltage, and you are able to get a quite good current with the reduced harmonics. So, lower than, typically you can call it lower than 11th harmonics are eliminated, and you have a band of 12 n plus minus 1. So, 11, 13, and that next set will be 11, typically your 23rd, 25th like. So, it is a series type 2 6 pulse converter or rectifiers are required in series at the output, and the phase shifting, I mean required the typically 30 degree from one to another, that is the phase shift required in the second transformer, and you require secondary line to line voltage typically maybe half, because you want to get like typically at the same voltage, I mean for the purpose, and turns ratio can be like a 2, or depends for one it may be 2 to 1, another case it will be 2 by root 3 because of the connection in delta, like star star and delta connection, and that is typically the you can think about how it is, and symbolically we can. So, the current of these two will be added here, it is you can see the current down here IA, here let us say again IA, because both are connected in series, but here it will be like IA dash and IA, typically another IA dash. The reason being why this current is, because this is coming from like a star connection, that is from delta connection. So, that turns ratio will differ for the 2 cases here to here like. So, coming to the waveform and fast Fourier transformation of it. So, you can just see clearly, I mean here we have a typically the load current which is almost like a DC, then we have a 1 6 pulse current where the fundamental is shown here, that is the typically another 6 pulse current. I mean you have both and you add it, then you will get this kind of current waveform, which is really the current drawn from the supply for a particular phase. And you can see the THD typically in 6 pulse converter, 1 6 pulse converter is 24%, another 6 pulse also 24, but that is getting typically get phase shifted, and when you add together, I mean you get 8.38. Ideally you are supposed to get, I mean like a typically order of 15% if the source inductance effect is not there, but if source inductance, because you are getting not that sharp. So, it is a because of the your source impedance, in the sense the leakage inductance of the transformer really help to improve the THD here. I mean in place of 15% or 15.5%, it is just going to half like 8.38% like. So, that makes the big difference. So, you can call it the fifth and there is no fifth and seventh harmonics in the line current, and the primary line current TAD is 8.38 in that. Well, the TAD and power factor, I mean you can just have it, I mean how the source inductance, if there is no source inductance you are going to have a typically order of, you can call it the TAD order of what you are getting here with the varying load, but if you have a source inductance you get the TAD reduction, I mean like if you have a 10%, I mean like a leakage reactance in per unit you get the TAD of this much corresponding to like at full load, I mean that's, so that is the TAD and this is the load virtually here, or the current in per unit you can call it like and however, I mean you will just see in spite of reducing the TAD, but this effect of leakage really have the impact on you can call it like a on the power factor, because that introduce some your displacement factor. So, it draws some, because of overlap angle it draws some reactive power, I mean from the supply, that is the reason power factor is going to be down with the load is changing like I mean or so. Now, you can call it the comparison with 6 pulse rectifier, TAD is reduced and power factor is improved, and this is typically the, you can call it the 18 pulse converter connected in series. You have 18 pulse converter where you require 3 converters, they are connected in series, and the phase shift here which we already discussed 60 by 3 because of 3 converter. So, you will have a your phase shift 20 degree. So, you have original star star and with the zigzag you are getting plus minus minus and plus 20 degree. So, that give you, because of the 20 phase shift you will get in 360 18 pulse 360 by 20. So, you will get a typically here the 18 pulse in the output of this 18 pulse converter like and that is how we are getting this phase shift with the help of zigzag connections like So, you can see the what is the kind of waveform. You have a 3 converters here, I mean like typically the 3 converters here and each converter have a TAD order of 23.7%, but in 18 pulse because of, I mean you are getting 3.06% in supply current, and why it is going to be, however ideally it should be 7.5 order of 18 pulse should be around 10 to 12% approximately, but in place of that you are getting 3%. So, this is the effect of leakage reactance, that you are getting very smooth current in that case, and you can call it the here the 5th, 7th, 11th, 13th are eliminated. The lowest harmonics will be 17th and 19th, and the TAD here is coming 3.06%. I mean like, well, the measured waveform you can say, I mean is available that okay, one 6 pulse, another 6 pulse, another 6 pulse with a phase shift of 20 degree from one to another and third one, and how it is the total current is coming in that way. So, this is for 6 pulse and this is for 18 pulse experimentally observed, and here also the effect of you can see, I mean on the TAD, I mean as you increase the leakage reactance of the transformer you can say call source impedance. So, the TAD go on reducing and full load you may find even very close to even order of 2% order of that, but this has a here the power factor reduces slightly because of the effect of your leakage reactance causes the overlap angle, and because of overlap I mean you get some reactive power burden and displacement factor get deteriorated, in spite the distortion factor is improving like I mean also. So, that is typically you can call it improved TAD, and this is typically case of 24 pulse series type of diode rectifier. So, here we talk about like you have a 60 degree phase shift divided by number of converter 4. So, it comes like a 15 degree phase shift, and this 15 degree you can find out here it is 0, then plus 15, then plus 30 and minus 15. There may be plenty of way, but that is the way how you can get with the zigzag and typically 30 degree phase shift. I mean here it is 0, here it is 30, in between you want to get 15 degree plus minus. So, that you have to use zigzag connection. Of course, there are many other connection possible also, and you are connecting all them in series. So, all will have a same current and these current will be all same, but when it gets reflected in the supply side all these current will be added together with the turns ratio, I mean correspondingly like So, you will get the here the quite good let us say TAD, and you can see how this is 4 converter, I mean 1 converter, second converter which have a TAD 24 per third and fourth converter with a phase shift of you can call it your 15 degree phase shift from one to another, and when you add together you get the TAD of this, and this is giving the TAD 1.49% by properly designing the leakage reactance of the transformer, which is responsible for providing the phase shift in this case like, and you can call it the lowest harmonics, it will be 24 n plus minus 1. So, if you take n 1 then it becomes the lowest harmonic 23rd, and the TAD here in place of 7.5 it reduces to 1.49. Ideally it should be 7.5, we discussed last time, but practically here you are able to get 1.49%, which otherwise ideal case this you could have gone even much higher than 96 pulse. So, that is the benefit you are able to get by adjusting the leakage reactance of the transformer, because transformer otherwise you are using. So, here also effect of your source inductance you are just going to that the THD is reducing, and but your power factor goes with the leakage reactance goes poor, because of the again you have overlap angle, and that causes the some reactive power burden on the supply side. So, displacement factor little bit deteriorate, but the or even the distortion factor improved, but displacement factor goes poor, and that is the reason you are getting power factor little reduction with the full load And or you can have a 12 pulse separate diode bridge rectifier. Many applications we have such things, but if you have a phase shift here, then it gets reflected on this side. If both loads are same, that also behave like a 12 pulse also. Or you normally there is an interesting example, you can say multi-level cascade edge bridge inverter, which have been, I don't know whether you have heard about, like a typically Rubicon drive, they have a like a 2 inverter connected in series for each phase. They are isolated because of this connection, and here you can see it is a kind of a like a 12 pulse connection. So, all these are 0 phase shift and these are 30° phase shift. So, for all 3 phases you need the separate secondary, and you can add the voltage there to get the multi-level waveforms which you can apply for this large rating. So, these are used normally in you can call it medium voltage drive of large rating of order of several megawatt or that, and you are getting typically like you can clearly get a 6 pulse this kind of the current, and when you add together in 12 pulse you are getting this, and the TAD here 30, here you are getting 7.36% typically corresponding to this 12 pulse converter. So, comparison with series type, the DC current ripple is higher and line current TAD is low too. So, the measured result you can see it is like a 6 pulse, and you are getting typically here by adjusting the leakage reactance, and these are the typically 6 pulse and this is the 12 pulse also. And the typically you can see how the leakage reactance is affecting the TAD. It is going quite low in that case, but the power factor you get little poor because of the you can call it the effect of this transformer leakage reactance as a source inductance, which causes the to like a overlap angle and cause the little reactive power on the supply system and this is typically for 18 pulse but you have a separate load for every 6 pulse and that can be, you can see all 3 converter how look like, and you have a TAD around 3% in place of, however each converter have a 32%, but you have a, because of capacitive filter it is higher, but when you combine together it comes only 3% TAD in 18 pulse converter and you can see here also the effect of your source inductance that reduces drastically the TAD quite down as you increase the source inductance or leakage reactance of the transformer, but your reactive power burden also increases, which causes the displacement factor to reduce. In spite you improve the distortion factor, but the overall power factor also reduce here and this is the case typically for 24 pulse converter, how the TAD reduces with the source inductance, and this is now the case of control bidirectional control converter, or you can call it 12 pulse thyristor silicon control rectifier, where you can control the firing angle for controlling the output power or the, let us say if inductance, so this current will be constant, and here you will have again typically 30° phase shift for 12 pulse So, it has a low line current harmonics and no SCR in series, and this is where it is used for variable frequency drive to so virtually it is driving a current source here for this current source inverter, PWM current source inverter, where you are using GTO and you are using the capacitor for making this PWM current here to make continuous current here. So, this also that is the example for variable frequency drive used for current source inverter fed drive and this is how the current typically you have a 6 pulse, another 6 pulse, how they translated, and finally how it goes to line current with certainly approximation that we are neglecting the leakage reactance of the transformer for analyzing this and now you can have a for analysis of this typically this current which you are having here in 12 pulse. So, you can have here this one converter of 6 pulse and other converter 6 pulse, and when you add this is typically you can call it in that case of your 30° phase shift, you will get they will cancel out each other, and when you will add together these two get modified, and when you add together you will not have 5th and 7th because their polarity is opposite. Okay. So, they cancel out, so 11th will be, but that 11th is also 1/11th that we discuss in, that is the benefit of multipulse converter, that I mean the harmonics go on reducing, I mean that is fundamental current, and this is you can call it 1 by 11 times fundamental. So, that harmonics go on reducing, and you will get the TAD if you add like all for 6 pulse. So, you will get 31%, but for I mean that is on primary side also, but when you go for typically that is for with 0 inductance, and that is on supply side of 12 pulse, and you will get typically I mean here the order of what is the order of harmonics coming up, and the TAD for this will be your 8.61%, however 6 pulse it is 24.6% like. And how it is the effect with the leakage reactance or the source inductance 0.5%, 10%. So, your TAD reduces, but typically you can call it with the firing angle the power factor reduces, because your firing angle certainly will cause the reactive power burden. As you increase the firing angle, I mean you will get your displacement factor poor, that is proportional to cos alpha, and you will have a reactive power burden also along with the harmonics. So, that is of course harmonics are reduced, but reactive power burden is there like because of this. And this is typically like your 18 pulse converter, control converter like a control rectifier, and here also you will add. So, harmonics will reduce, but reactive power burden with the. So, you can see 6 pulse another 2 6 pulse and how the current added in 18 pulse, and the TAD here for 6 pulse is 24 point, it's a harmonic spectrum. So, 24.6, but here you can call it in case of your 18 pulse is 3.54% like, and the how it is affecting by the leakage reactance the harmonics also, and however typically you can say because of the your firing angle the power factor gone reducing, TAD is not too much affected by, it is affected, but that is because of the your source inductance I mean is less in that case, and that is for 24 pulse converter you are using 4 bridge control 1 I mean like, and here also you can say effect of leakage reactance on TAD, but here it is firing angle effect, the power factor go typically TAD also affected by firing angle like. Now, coming to analysis of isolated fork connected transformer based ADC converter, that is the typical example for 6 pulse, that is star delta. I mean, but for higher number of, if you want 12 pulse, so you have to have plus minus 15 degree. So, you get from the fork connection delta to star, but fork connection on both the side to get like a symmetrical, I mean you can call it output, and then you get a 12 pulse. So, that is for kind, and for 18 pulse 24 pulse you have again the 4 voltage, that is plus minus 7 point and then plus minus 22.5 primary side is your delta. So, you are able to get phase shift, and you are able to connect them either in series or parallel. So, you I mean many applications you may not like to increase the voltage, they connected parallel, but with the interphase transformer like. And how did the transformer connection, clearly you can see with the proper phase shift also, and how the phasor representation is there for, this is for primary, this is for secondary, or plus minus 7.5% from original of course, and then you have a 15 that is 22.5 degree, 22.5 degree, you get the 4 phasor, or you get your 4 3 phase supply with the phase shifting or phase staggering like for this, and that is the typically how we are going to have the design of that. I mean these are the voltage requirement, and then you are able to get from this phase shifting with the help of this relation, where you can get the value of K1, K2, I mean all these constant from here for these phase shift, and you can find out the even a KV rating also similar to what you are really get in 2 winding transformer, and then transformer utilization. So, this is typically MATLAB model of that, and transformer MATLAB model, and these are the performance like for 24 pulse. You can see the TAD typically of 12 pulse at light load, ideally it should be like a 15% if no leakage reactance is there, but it goes even reduced from not 15, 9.2%, and here in 24 pulse we expect 7.5, but because of leakage it at full load it goes 2.7% or so like, and that is typically you can call it comparison of 6 pulse then 12 pulse, and how it is the typically the TAD is 24 to 9.24, and then it goes to typically your order of 2.7. So, effect of leakage I mean really gone making the current closer to sine wave with higher number of pulses like, because even a small overlap angle really makes a reduction in TAD for higher number of pulses like, and that is typically like of 6 pulse, how it look 3 phase current with the supply, and you have a TAD 24% with effect of leakage reactance, and then typically your 12 pulse I mean it is a 9.2, and how 3 phase line current looks like, and then your 24 pulse your TAD reduced 2.7% of this current, which are 3 phase current here along with the input voltage and output current, DC current and DC voltage like, and that is the typically the rating with the isolation. Certainly the rating will be more than 100% here, Why it will be more than 100%? Because you are not feeding the sinusoidal current either in primary and secondary. So, that caused little increase in the your transformer rating even for 6 pulse, where you have only isolation transformer. But for 12 pulse you require interphase also, interphase transformer, as well as for 24, and your rating is typically for 12 pulse and 24 pulse, how it is the magnetic rating of this transformer along with the interphase transformer rating, like as a percentage of the load rating. This is typically 36 pulse converter. I mean, you have a here 18 pulse, another 18 pulse, how you really getting with the fork based connection of this transformer, like, and this is typically how the transformer connection is there primary, and secondary you are getting for typically for 18 pulse, one set of for 18 pulse, another set of 18 pulse. I mean, you are getting with the kind of your phase staggering, and even the you can call it like a 3 single phase transformer. I mean, with several winding can do that job. I mean, because these all, let us say, vertical is on here on one transformer, I mean at different angles, where you have another transformer and the third transformer, how it is the your connection is taking place. And this is the phasor diagram, which all the points should be on same circle to make a same RMS voltage on the secondary side, but you are able to get the phase shift corresponding to like a your plus minus 5 degree, that is 10 degree phase staggering, because you need the 36 pulse means 360 by you can call it the 360 by 36, so it is a 10 degree. So, you have a phase shift only 10 degree plus minus 5 degree, then typically for another set similarly you will get another set, I mean of the phase shifting of that to get, and these are the calculation for the transformer, I mean the how you are getting phase shifted voltage, and these are the constant calculated as a percentage. So, that is for virtually concept of design of this transformer. This is the model of the converter along with the transformer, and this is the transformer model in MATLAB, and these are of course simulated result, and you can see the TAD how it varies for 36 pulse converter, I mean starting from 3% to it comes like 1.197% like, I mean, and it means if you want a TAD less than 3%, I mean like you have to adopt the more than 36 pulse, which is required in Navy application either in Indian Navy or even in US Navy too, and that is typically the comparison that how you are getting the typically the TAD from here 27 point, and here you are getting typically order of 3% like or so, and power factor close to unity compared to here like because displacement, and this is the typically the you can call it current in different winding. So, this is supply voltage, supply current, and you can see the current in different winding how it is there, like including the interphase, and you are getting the final current DC on the load side if you have the winding current distribution, and that is typically the input voltage, input current is in phase with the supply voltage and sinusoidal, and the output voltage, output current, and this is the TAD harmonic spectrum, and the TAD around 3% of this 36 pulse converter, and this is typically your at full load, I mean only you are getting 1.19%, you can see supply voltage, supply current and current waveform with output voltage, output current like, and these are of course this is was also developed in the laboratory. So, we get the you can call it the TAD order of at light load, I mean order of 2.3, but at full load which is this was 20%, you are getting only 2% like here the TAD, I mean in case of this 36 pulse converter, and you can have a magnetic rating 6 pulse, you do not need the interphase, but you can see because of the current quite distorted current you are getting 8% more rating 108%, but in case of 36 pulse you are getting of course higher rating, and this is interphase rating, and you get 125% rating of the transformer or magnetics like common here like, and this is the typically how the typically with the load is your TAD of the current is changing from 2.3% to 2% in this typically in 36 pulse converter. So, here this the proposed 36 pulse converter is live by 2.2 kVA single phase transformers, and the details are given here at which these are designed with the current density and flux density, and how the turns per phase like it was just simply given to the manufacturer, and these are the turns designed from constant, okay, and the wire gauge correspond to that much current or so. And while coming to analysis of T connected isolated transformer, this is you can see how the T connected. So, T connected we are applying 3 phase balance supply, we are getting 3 phase balance supply. So, very purpose of this is just to provide isolation with the typically of scaling the voltage what voltage you want for rectifier, that is T connection for 6 pulse, and this is how the current look like because of leakage. It is not Courtesy square wave, I mean it is goes to the typically of not the sharp notches here, and TAD in place of your 31% it goes 23.89% because of the source inductance like, and this is your 12 pulse. So, what we are getting for 12 pulse here again T connection, and here also phase shifting of plus minus 15 degree taking place from original voltage and other also plus minus 15. So, you get the 2-3 sets voltage which are 30 degree phase apart. So, they are virtually original is plus minus 7.5%, you get a 12 pulse converter from this T connection. The benefit of this that you are only using typically the 2 single phase transformer here, one is vertical, another is horizontal with several winding which you are having for primary and secondary. And this is 24 pulse, you are having 12 pulse, and with this pulse doubling with the help of transformer interface you are able to get 24 pulse configuration here. So, it only needs the 14 diodes, not the 24 diodes. So, that is the benefit of this but of course, additional losses of the additional diodes in series within place in addition to the 2 diodes here and that is the typically of how the T connection design is there. Okay, you have a one horizontal and vertical, that is the typical. Neutral you do not need, but here you require the neutral just to equalize the voltage all, and this is how you are getting a phase shift. Typically for 12 pulse 30 degree phase shift with the plus minus 15 degree for one set of winding, another set, another. So, you have a one and this another as a one 3 phase, another side of another 3 phase and this is the typically the model total system, and this is the transformer connection model, and these are the currents typically in case of the your 12 pulse 3 phase currents down from the supply, and the TAD of this is the order of 6.14 in place of 15% because of the effect of leakage reactance of the transformer. And these are of course for 24 pulse with pulse leveling, and the TAD reduces to order of 3.5% in place of 7.5 because again effect of the leakage reactance and your current goes very close to the sinusoidal also. And this is typically for 12 pulse how the TAD changes from the load from 9.6% to 5.4 and for 24% per pulse virtually for your 5.46 to 3.5% also. And then typically 12 and 24, if you compare all three for your full load, the TAD reduces to 6 to 12%, 24% to 6.1, and then further you reduce to typically order of 3.5% also. Well, coming to now the numerical examples on these multipulse converter. So, a DC load of 1.2 kV 500 volt ampere is supplied by the 12 pulse thyristor bridge rectifier at 30 degree fire angle of their thyristor as shown in the figure. Calculate A required thyristor rating and the transformer secondary voltage with the primary applied 3 phase supply voltage of 415 volt at 50 hertz for series connection of 2 thyristor bridges. B the current in each winding of the transformer. C the kVA rating of the transformer, and D the supply current RMS and its TAD. So, these are the typical connection that you have a star and delta star and 2 thyristor bridge connect which are connected in series with have a common current of IDC. And coming to numerical part of the given supply voltage of primary 415 volt and frequency of 50 hertz, and the load we require load current of 500 ampere and the voltage of the load is 1.2 kilovolt. So, you certainly need a transformer of a step up in that case. So, you can just see because both are connected in series. So, to get the 1.2 kilovolt, so each converter should give you around 0.6 kilovolt 600 volt, and you can find out typically from the relation that how much you need the secondary voltage. For given a fire angle and you are given a required DC link voltage, okay, you can find out the line voltage, and this line voltage at the secondary of the transformer you need this much in place of your 415 from the 415 volt. So, you are able to get typically the line voltage of the secondary side is by root 3. So, you get 296.19 and the peak inverse voltage of the thyristor where you are connected you get root 2 time line voltage that is 725.51 volt, and the secondary side transformer connected in delta the phase winding voltage is 513.019 and the current in the secondary side will be where DC link current is given 5 ampere. So, RMS current will be root 2 3 by 346 pulse converter. So, you will have a 408.24 ampere, and then you can get the current typically on the line current of secondary of the delta also, and typically you can have a phase winding current of the delta connected, and from this turns ratio from voltage you can get turns ratio, and this is the typical turns ratio of the two transformer. One is for your star star, another is star delta, and then these are the typical simulated waveform of supply voltage, supply current of 3 phase, then the 6 pulse converter, and this is the per unit current on primary side. These are all secondary, this is on primary side, and then this is your you can call it like a DC link voltage of 1.2 kilovolt and the 500 ampere load current and these are the typical. Now, from this you can find out the what will the from secondary current which are known to you, you can find out the primary current magnitude, and for kVA rating you have to include all the voltage and current of each winding with the half, because even normal transformer also you take either primary or secondary, but here we take a relation half of your typically volt ampere relation for all the winding. So, you have a delta primary, you have a star secondary and delta secondary, and 3 of that for 3 phase and 0.5 into 3. So, you get typically for this your kVA of the transformer 713.726 kVA, and the TAD I mean you can find out from the current from different harmonic spectrums you get 15.23 or so. Now, coming to a second example, a DC load of 1500 volt 300 ampere is supplied by 18 pulse diode bridge rectifier, and calculate the required diode ratings and transformer secondary voltage with primary apply 3 phase supply voltage of 415 volt at 50 hertz for series connection of 6 pulse converter, B the current in each winding of the transformer, C the kVA rating of the transformer, and D the supply RMS current and TAD. And this is typically the connection of your typically of because of zigzag you are getting for 18 pulse. I mean they must have a relative angle of 20 degree, and because from here to here you are getting typically 7.5, then 20 degree leading, 20 typically lagging from this, and all 3 bridges you are connecting in series. So, that is a one way of getting this. So, coming to numerical part of this, given supply voltage of 415 volt frequency of 50 hertz and DC load of 300 ampere and voltage of DC load is 1500 volt. The total DC voltage across the series connected diode rectifier is 1500 volt. So, the DC voltage across each diode bridge rectifier will be by 15 by 3 500 volt, and for 500 volt output you can find out what is the line voltage for zigzag transformer, that comes at 370.2 volt like, and for that you can find now from line voltage you can find peak inverse voltage of the diode rating, and then you can find out the diode current typically secondary zigzag transformer current, and you can have a transformer turns ratio for all the 3 zigzag transformer. And after putting all these values, the model is developed of this system, and these are the typical supply voltage 3 phase current and 1 phase current, then 6 pulse converter current, and then the output voltage and typically the output current like, and these are the typical numerical values. So, you can find out the primary current from all these 3 currents with the proper respective of their phase angle, and you get the primary current this much. Now, you have to find out a kVA rating. So, that is 3 times your voltage rating of winding, current rating of the winding, and you multiply it and put the all value. So, you will get the rating kVA rating of the transformer 461.5 kVA, and total harmonic distortion of the primary current, if you get all the harmonics from that current waveform which are shown there, you get around 10.09% like. So, now coming to example 3, a DC load of 2.4 kilovolt 100 ampere is supplied by a 24 pulse diode bridge rectifier as shown in figure. Calculate the required diode rating and transformer secondary voltage rating applied to 3 phase supply of 460 volt 50 hertz for series connection of the converter. The typically your current in each winding of the transformer, and C the kVA rating of the transformer, and D the supply current and its total harmonic distortion like. So, this is the 24 pulse converter which 4 bridges are connected in series, and you get the phase shift here with the zigzag connection. The phase shift should be like a 15 degree 7 plus 7.5 minus 7.5. So, it is a 15 degree between 2 bridges because it is a 4 bridge. So, 60 by 4 degree by 4. So, it become your 15 degree. Okay. That is the 15 degree we are maintaining between this and this, and from this to this and this to this like. So, coming to numerical part of this, given data, the DC load current is 100 ampere and DC load voltage is 2400 volt, and primary 3 phase voltage is 460 volt and the frequency is 50 hertz. So, total DC voltage connected diode bridge rectifier is 2.4 kilovolt. So, your DC voltage for each single phase diode rectifier is 2.4 kV divided by 4, so 600 volt, and you are able to get for this output 600 volt the line voltage required for the secondary of the winding. From this relation you get 444.288 volt like, and now the peak inverse voltage from secondary line voltage by into root 2. So, you get 628.31. This is the diode rating peak inverse voltage, and then you can have a zigzag current from the DC link current from this RMS current, and then you can get the transformer turns ratio, and after putting the value or making the model of this total system. This is supply voltage, supply current for 24 pulse converter, and this is one line current, where we are neglecting the leakage reactance to get test calculation for simplification. And this is the 1/6 phase pulse converter current, then your DC current and DC voltage like. So, coming to now RMS calculation of primary side. So, you have all 4 winding current here, and the current comes 302.052 ampere on the typically on the primary side. Now, you can find out the kV rating, where you have to consider each winding with the current each for all the typically 4 secondary winding and 1 primary winding, and this comes to 45.977 kVA. And the TAD of this current you can find out from the waveform, it comes 7.57 percent, because you are considering ideal current with the stepped waveform like. Now, coming to example 4, a DC load of 3 kilovolt 150 ampere is supplied by a 30 pulse bridge rectifier as shown in the figure. Calculate a required diode rating and transformer secondary voltage with the primary 3 phase voltage of 440 volt at 50 hertz for both for series connected 6 pulse converter, and typically the current rating in each winding of the transformer, kV rating of the transformer, and supply current, RMS current, and the TAD. This is for 30 pulse, 30 pulse, you have a 5 converter for 30 each of 6 pulse. So, that will be certainly 60 divided by 5. So, you will have a 12 degree phase shift, okay, and you will find here the 12 degree phase shift among the near 2 consecutive like, and all are connected in series. So, you have a same current, and this is the primary connected in star like. So, given data, the DC load current is 150 ampere, the voltage is 3 kV, and the primary voltage is 440 50 hertz, and the total voltage across the series connected with 3 kilovolt, and we have a 5 bridges. So, each will have a 600 volt. And now, for giving output voltage 600, you can calculate the secondary line voltage, that is come again 444.282 volt, and the PIV rating of the diode you can find out root 2 times the line voltage, that is 628.31 volt, and you can find out the secondary zigzag current from DC link current, it comes 124.47 ampere, and that because of zigzag connection this is the same as the winding current, and from that you can now find the typically, because we got the line voltage of primary and secondary. So, you can have phase voltage and phase voltage secondary. So, you can get a typically the turns ratio for all the typically of 5 transformers secondary, and after making the model with these data we are able to get the waveform supply voltage. This is the 3 phase supply current, this is the 1 phase supply current, and this is typically 1/6 pulse converter current, load current, DC load current, DC link voltage. So, now putting the getting a primary current in star. So, you have a current from all the secondary winding reflected to primary with the proper phase shift, and you get this current corresponding to 590.324 ampere. And for kV rating you have to take VA of all the windings here and putting their respective value, and by 2 of that. So, you get 460.55 kVA, and the TAD from this you have to put all the individual harmonic which are there, because it is typically your 24 pulse. So, lowest will be 23, and you have to consider dominant only. So, it comes 6.05% like also. So, now coming to 5th example, a 12 pulse diode bridge converter feeding to a RL load of 50 kilowatt as on the figure. The input supply is 3 phase 415 volt 50 hertz. Consider the phase shift between 2 consecutive voltage of plus minus 15 degree with respect to the input voltage. A, calculate the number of turns in different winding of the outer transformer for achieving 12 pulse operation. B, calculate the current in each winding of the outer transformer, find the DC link current, supply RMS current, and its total harmonic distortion. So, this is typically the connection for getting from 3 phase supply your typically 12 pulse converter, 2 phase shifted converter with the interphase transformer. So, we are able to get phase shift like a plus minus 15 degree, that is 30 degree phase shift here, and this is typically the relation, you can call it 3 phase supply voltage 415 volt 50 hertz and DC load power 50 kilowatt, and the input diode bridge rectifier have a plus minus 15 degree phase shift, which we discuss it. So, for that you can have a relation to get these constant K1, K2 for winding, and these are the 3 sets of voltage original, and this is 2 phase shifted plus 15 degree and minus 15 degree, and then putting the value for this voltage you can find out the constant K1, K2 which provide the plus minus 15 degree phase shift, and you get the value of K3 also, and from this you can find out the even the now the typically the DC link voltage, and you can have a all 3 typically the DC link voltage equal for both the bridges like, and after making the model, this is the waveform of supply voltage and all 3 phase currents. Because of leakage, they are very 3 phase supply voltage, and this is a load voltage, load current, and this is the typically 6 pulse converter current of 1 and taken, and this is the typically your line current like. And coming to the calculation, load current you can find out from power divided by the DC voltage, say comes 89.21 ampere, and you can find out the RMS diode bridge current typically of all currents, that is root 2 3 by ID for 6 pulse, and then considering the power neglecting the losses, considering primary input power to equal power, and you can find out from this typically, because here you do not have a any reactive power burden because of diode, and we consider displacement close to unity. So, we can have power point and we can find out the line current from this relation. So, that comes 69.56 ampere, and I1, I4, I7 are the input current of the auto transformer, and from that we have a all winding current now from here. So, we can find out even the current in the primary side. So, this is the current, and now of course, you can find out from different harmonic current the TAD of 15.2. Now, coming to example 12, a 12 pulse, example 6, a 12 pulse diode based converter is feeding power to the RL load of 75 kilowatt, and input supply is 3 phase 460 volt 50 hertz. Consider the phase shift between two consecutive voltage plus minus 15 degree with respect to input voltage. Calculate the number of turns in different winding of the output transformer achieving 12 pulse operation. Calculate the current in each winding of the output transformer. Find the DC link current, supply RMS current and TAD. So, that is the typical connections like for getting a I mean you can call it is a umbrella kind of connection. You are making like a tapping for giving input supply, and then you are raising the voltage, and then you are having a plus minus 15 degree phase shift for getting 12 pulse converter, and this is the typically your interface transformer, the load is connected. So, coming to the solution of the 3 phase supply voltage of 460 volt 50 hertz, and the load diode is the bridge rectifier, and input voltage of diode bridge rectifier has plus minus 15 degree phase shift from the input supply voltage of. So, we get the relation corresponding to phase shifted plus minus 15 degree from original voltage, which is sum of the 3 voltage as you have seen in the winding connection, and just putting the phasor for first, then 15 degree leading, 15 degree lagging. So, and this is the typically the phase voltage from the line. So, we are able to get K1, K2, K3 constant from the design, and then we can, once we know the voltage applied, so we can get your DC link voltage, and then we can get the current in the load once we know the typically power and the DC link voltage. So, we get the DC link current, and after making the model, this is your 3 phase supply voltage, these are phase shifted voltage, and this is the DC load voltage, load current of DC side, and the 6 pulse converter of 2 separate with the phase shifted, and this is the line current typically finally in the this 12 pulse converter, and these are the current virtually you can call it for the winding from the DC link current, which is quasi square wave for 6 pulse, and considering the power same on both sides, you can get the line current typically of your this much ampere in all winding. And now you can find out from this the typically the winding in all winding currents from here, different winding current from the relation, and then you can have a total harmonic distortion from different currents from that waveform, it comes 15.23. Now, coming to example 7, a 12 pulse diode bridge converter is feeding a power to the RL load of 25 kilowatt, and the input supply 3 phase is 460 volt 60 hertz. Consider the phase shift between two consecutive voltage of plus minus 15 degree with the respective input voltage. Calculate the number of turns in different winding of two transformer for achieving 12 pulse operation. Calculate the current in each winding of auto and find the DC link current, supply RMS current and its total harmonic distortion. And this is another connection for getting a 12 pulse of plus minus 15 degree, which call it extended delta. This is auto connection, and because of that we have 6 pulse, but we have interface transformer, so that the circulating current is avoided like also. And so, power rating is 25 kilowatt with 3 phase line voltage of 460 volt at 60 hertz, and we have here now the winding voltage like typically for A phase, which give plus 15 minus 15 degree, and then you have one set original supply, then your this other set voltage in terms of supply line voltage, and from this you can get auto connection the typical example from that K1 constant corresponding to the your tappings, and then you can find out the short winding turns ratio from here, and then you can have a turns ratio in the primary side corresponding to root 3 times because of the your star connection, and then you can have a typically the voltage related to for those winding here as shown in the phasor, and then you can, once you know the line voltage applied to the rectifier, you can find out signal converter, you can find out the DC link voltage of 1197, and then after making the model you have a 3-phase voltage, then these are the phase shifted voltage and DC load voltage, DC link current, and 2 12 pulse converter current and final current on the supply side. And these are numerical calculation that you have a DC link voltage 1197 volt and you have a DC link current once you know the power and typically of, and then you can have a all winding currents corresponding to different diode bridge rectifier, and then you have, considering the power equal, you can find out the typically even the, you can call it line current on primary side. And then you can find out RMS current is known to you, and you can find out the typically fundamental current, so you get 15.23% TAD like. So now coming to the your example 8, an 18 pulse AC DC converter, base converter is feeding power to RL load of 15 kilowatt, and the input supply voltage is 3 phase 460 volt 60 hertz. Consider the phase shift between the two consecutive of plus minus 20 degree with respect to the input voltage. Calculate the number of the turns in different windings of the auto transformer for achieving 18 pulse operation. B, calculate the current in each winding of the auto transformer. C, find the DC link current, supply RMS current. C is total harmonic distortion. And these are typical transformer connection to get virtually one is original connected to original one, middle one, and there is 15 degree, 20 degree leading and 20 degree lagging. And with this interphase transformer we have to connect, because we are connecting them in parallel. So this give us like a operation of 18 pulse like. And coming to numerical part, the solution given 3-phase supply of 460 volt and the power is 15 kilowatt and frequency 60 hertz, and the input voltage of diode be required with the plus minus 20 degree phase shift from the supply. You can have a phase shifted from these constant from adding the voltage corresponding to the phase voltage, and these are the 3 sets, one for original, another 20 degree leading, 20 degree lagging, and from that of course you can find out the what is the phase voltage from the line voltage, and then from this you can get from this relation what voltage you want. You can get a constant for turns ratio, all 3 K1, K2, K3 which are shown, and you can find out once you have a here the line voltage as the rectifier input, you can find out easily the your rectifier output DC voltage of 621.22 volt, and this is same for both because both are connected in parallel, and you can find out from power relation, power divided by DC link current. So, you can get the DC link current also of 24.15 ampere, and from this you can make a model and you get the 3-phase voltage, then the phase shifted voltage, then load voltage, load current, and 3 converter current and total current like. And coming to calculation, that you can calculate the different winding currents from this relation from DC link current, and considering the power invariancy you can get the line current calculation here that is also flowing in some of the winding, and for remaining winding you can calculate from the basic relation of Kirchhoff's current law the current in different winding like typically even line of, and from once you know that the waveform you can find out the total harmonic distortion from different harmonic current, that comes 10.09%. Coming to example typically 9, a 18 pulse diode bridge converter feeding a power to RL load of 25 kilowatt as shown in the figure. The input supply is 3 phase for 15 volt 50 hertz. Consider the phase shift of 2 consecutive output plus minus 20 degree with respect to the input voltage. A, calculate the number of turns in different windings of the output transformer for achieving 18 pulse operation. B, calculate the current in each winding of the output transformer. C, find the DC link current, supply RMS current, and its total harmonic distortion. So, this is typically the connection for 18 pulse configuration with plus minus 20 degree phase shift with this fork kind of, typically the umbrella kind of connections. So, one we are typically taking original, another is we are giving the phase shift with respect to that, but we are making sure in design that all the voltage are on the rectifier input are same magnitude like. With the why we have to use interface transformer, because we have to distribute the current in all the 3 bridges like. So, for this given the 3-phase supply of 15 volt 25 kV and 50 hertz. So, we can have a phase shifted voltage here typically of plus minus 20 degree, and this is your what you are getting here 20 degree leading 20 degree lagging with respect to 0, and then you can find out the typically the phase voltage from line from supply, and then you can get the constant corresponding to the winding turns ratio K1 K2 in that to get particular phase shift of plus minus 20 degree. Then once you know the line voltage at the input of supply, you can get the DC link voltage 560.44, and you can find out both will converter will give equal, all 3 converter will give same voltage because they are connected in parallel, and you can find out DC link current form typically from this relation. And after that, this is typically the supply voltage, and these are the phase shifted voltage of 3, one original plus minus 20 degree, then DC link voltage, DC link current, and 3 6 pulse converter current, and sum of that to have a line current like. And then you can find out the current in all the winding of the in terms of the DC link current, and then you can find out the typically the line current corresponding to that, and then from Kirchhoff's current law you can find out the current in other winding. And once you know the waveform, you can find out the harmonic spectrum and TAD of this. Now coming to 10th example, 12 pulse diode bridge converter is feeding the RL load 15 kilowatt as shown in figure, and input supply 3 phase 415 volt. Consider the phase shift of plus minus typically of 30 degree. Calculate the number of turns in different winding of auto connection to 12 pulse of frequency. Calculate the current in each winding and DC link current and supply current TAD. This is the connection for 12 pulse converter. We are getting typically 0 and 30 degree, for phase shift for 12 pulse, that is another connection. And for given that, we are just making the relation for phase shifting here. For 3 phase, another set of supply, one is original phasor, another is 30 degree phase shifted one, so that we can get the your 12 pulse operation, and this is the phase voltage, and then we can get the design constant corresponding to the getting number of turns for getting this phase shift K1, K2 and K3, and then from this we get the DC link voltage, and all typically both DC link voltage will be equal, they are connected parallel, and we get the DC link current. And then we can from this we can get different winding current, and then we can find the line current from this typically power relation and the all winding current, and then we can get the TAD from here like. Now coming to summary of this multipulse converter, improve power quality multipulse converter to comply with the stringent harmonics requirement. Major higher power drive manufacturers are increasing using multipulse AC/DC converter at front end, and the main features of multipulse AC/DC converter lies in its ability to reduce with the line current harmonics distortion, and higher the number of rectifier pulses, the lower will the line current distortion. And broad classification of conventional multipulse converter is discussed, and their comparative harmonic performance is also analyzed in this topic. And the line current TAD of the 12 pulse converter normally do not satisfy the harmonic requirement to specify by IEEE 519 standard. So 18 pulse converters have better harmonic, while the 24 pulse and higher number of pulses provide a good harmonic profile. And detailed design, performance analysis and comparative evaluation of multipulse AC/DC converter based isolated fork connection T connection transformer has been presented, and these are the references. Thank you.